Okay, now you're on camera chatting, I think. Who can see? Can you see the recording thing here?
Yes.
Okay, everything's fine. All right, ladies and gentlemen, here we go. We're going to be talking about heat, enthalpy, and calorimetry. Shh. When you have a chemical reaction that occurs in an open container, most of the energy that's gained or lost in the reaction is in the form of heat. Remember that heat is the transfer vehicle for thermal energy. All right, we recall from a lot of our vocab work that almost no work is done. Remember, work is equal to a force acted upon over a distance. Okay, there is no distance, but we can talk about a force being pressure. Pressure is a force over an area. Okay, that is some work that's done in chemistry. So when you're talking about chemistry, the only work we're talking about is pressure. So if the container is open, there is no pressure gradient because it's equilibrating from the start to the finish. So there is no pressure, so there is no work. Now, we do have heat flowing between the systems and the surroundings until they come to the same temperature. When they come to the same temperature, it is said that they are at thermal equilibrium. Okay, so one of the things that you recall from your reading is that heat always goes from hot to cold, despite what you think, from hot to cold. The SI unit that we'll be using when we talk about heat is a joule. A joule is a teeny tiny unit. Most likely we'll be talking about a kilojoule. Okay, here is this new word for you that we are going to discuss. It is called enthalpy. Now, when we have constant pressure, that would be in an open container, the heat gained or lost by a chemical reaction is termed enthalpy, or heat content. All right. The change in enthalpy, delta H, is equal to heat, which is Q. So here we go. So we don't have to write enthalpy all the time. We have used the abbreviation delta H. So we don't have to write heat all the time. We have used the abbreviation Q. So when you have a constant pressure, the change in enthalpy equals heat. All right, enthalpy is a weird duck. It cannot, first of all, the unit is in joules. It cannot be measured directly. You cannot put something on a balance and say, okay, this has this many joules of enthalpy. One of the reasons why is it's a constant change between the system and the surroundings. This is a dynamic process. Okay, enthalpy is a state function. That means the pathway doesn't matter. Here is an example of a state function. How many of you would agree that you are all here right this moment in time? Pretty much all of you would agree. Okay, I know the pathway that I took to get here today. And I am fairly confident none of you started out in my kitchen this morning and took the exact same pathway that I did to get here. So
I had to follow.
We all got here, but we got here in a different manner, yeah? So the enthalpy that you arrive at will be the same, but you can get to that delta H value a number of different ways. The biggest way, the actual equation is the enthalpy of a reaction. The enthalpy of a reaction is equal to the enthalpy, let's put the change in enthalpy of the products, minus the change in enthalpy of the reactants. Always products minus reactants. products minus reactants. If the value that you compute for the delta H of reaction is a negative value, that means it's an exothermic reaction. An exothermic reaction. The products have lower energy than the reactants. So your little memory hook for an exothermic reaction is it is a step down. Step down. Energy is being released. Heat is being released. Delta H is negative. The products are more stable than the reactants just by virtue of the fact that the products have lower potential energy. If you have something that has a lot of potential energy, it is not very stable. Someone who is very high maintenance, has a lot of potential energy, is not really stable. I just made that up. Could you tell? Okay. Delta H is an extensive property. An extensive property means that the amount under study matters. Delta H will vary depending on the size of the sample. Write that in your own words right now. Delta H for the opposite reaction. Here's my favorite reaction. If this is the delta H for this direction, then the delta H for this reaction will be the same in magnitude. That means the number is the same, but the sign is opposite. So if this is exothermic, this will be endothermic. To look at an endothermic graph, that's a step up. Heat is absorbed. Heat is going in. The reactants are more stable than the products. Okay, I want to make something crystal clear that we worked on in the vocab. Remember, we talked about the universe, and the universe is composed of two things, one of which is the system, and the other is the surroundings. The system is defined as the thing under consideration, the thing under study. And the surroundings are everything else. All right. Now, I want to talk about these terms, which this one is heat. And this one is, I want to talk about the signs of Q and the sign of H. Okay. Now, in chemistry, which is different than the way it is in most of physics, but in chemistry, we are looking from the perspective of the system. The system and us. Here we are. We're looking through the same eyes as the system. Got it? So if we are talking about energy or heat leaving the system, that's a loss. And therefore, the sign will always be negative. If we are talking about heat arriving, that's a gain, and the sign of Q and delta H will always be positive. So if we have an exothermic is a negative Q, a negative delta H, that means that heat left the system, and where did it go?
To the surroundings.
To the surroundings. If we have a positive value for delta H or Q, that means it is an endothermic reaction, and that means heat entered the system from the surroundings. Okay, now I need you to be very clear on this because we're going to be talking about enthalpy, and I'm going to be using the words energy and heat and all sorts of stuff. Is there such a thing as negative energy?
Aye.
Is there such a thing as negative heat?
Aye.
Also not. Right. The sign in thermodynamics, here, write yourself a little asterisk. The sign indicates nothing more than the direction of flow. So if you were so inclined and you decided to leave off the negative sign for your Q value, you would get total points if you said, let's say, 1,450 joules left the system to the surroundings. You can make a shortcut to that and just write negative 1,450 joules, and we'll all understand what you mean. You get? The sign indicates nothing but the direction of flow. Okay, now let's get back to delta H. The change in enthalpy can be calculated a number of ways, all of which will probably annoy you. You can do it stoichiometrically, by calorimetry, from tables, which I will give you in a moment, from Hess's law, which are puzzles for smart kids, and from bond energies. Right this moment in time, circle a gazillion times. If you are one of those people with a highlighter, highlight now, because bond energies will be the weirdo. And when we get there, I'll tell you why. Okay. Sample problem A. Upon adding solid potassium hydroxide pellets to water, the following reaction takes place. Right this moment in time, please identify the system in this problem. Okay, this would be the system. All right, and the surroundings would be anything that's in the cup, probably the water as well. Okay, answer the following questions regarding the addition of 14 grams of KOH to water. First of all, it says this. What does that mean? Releases. If you were to sketch the reaction coordinate, that's those graphs that we had on the other page, where this would be potential energy and this would be activity, time, the pathway. Tell me, would this be a step up or a step down?
Step down.
It would definitely be a step down, where these would be the reactants and these would be the products. You know that because this energy is exiting the system. So it's out of there. It's a step down. This is an exothermic reaction. Okay. Now, the beaker is what part of the universe?
Surroundings.
Surroundings. The system is giving off heat to the, so the surroundings are feeling, there you go. We have determined it is exothermic. What is the enthalpy change for the dissolution? Dissolution is a fancy term for dissolving of the 14 grams of KOH. Seems to me there could be a math problem here. Here's another way to think of delta H values are generated per mole. So the delta H is 43 kilojoules per 1 mole of KOH. Well, now I think I can do something with this. I think if 43 kilojoules are released in 1 mole, I want to know how many kilojoules are released in 14 grams worth of KOH moles. I need to know the number of moles equal to 14 grams of KOH. 1 mole of KOH has a molar mass of 56, so that's 1/4 of a mole. So 43 released in 1 mole, how many in 0.25 moles? And the answer is 10.7 kilojoules released. Now, would I get full credit if I wrote that?
Yeah.
Mm-hmm. Or you can shorthand it minus 10.7. Okay, let's talk about calorimetry. All right, we just did a stoichiometric way to calculate delta H. Now we're going to talk about calculating delta H when we're doing calorimetry, which we will do on Friday when you need all your safety gear.
Wait, Miss Adams. Bottom says that it's warmer and.
It's
Never mind, that's what we did.
that's
but,
correct.
no.
Okay. Calorimetry is based on a heat from the going into the solution. Okay, so heat lost by the system is being picked up by the surroundings, which is solution, or the solution will provide heat to the substance. Got that? No. Okay, here, look, I already made one for when you do this on Friday. It is very complex. It is 2 coffee cups, which are kind of insulating. You'll take the temperature of 2 different liquids. You will average those temperatures to get your initial temperature. You will mix them together, pop the top on it, and wait to see the highest or lowest temperature that you get. Got it? Okay. That is your delta H. Okay. Now, the problem with that is it's just a tad more complex. The temperature change when there is a chemical reaction. Get what's happening? In this case, we're going to be using HCl and NaOH. They are going to react and form. And energy will either be released by this reaction or absorbed by this reaction. We're going to assume, and this is a faulty assumption, but we're going to assume it anyway, that no heat will leave our ghetto calorimeter. All the heat that is either evolved, that would be released, or absorbed, will be contained within the calorimeter, and we will be able to measure that by measuring the temperature. Now, the thing that we have to remember is that Q, the heat, is extensive, so it does depend on the mass of the solutions that we're using. And then it also depends on C, because every substance in every phase of every substance has its own specific heat. The amount of heat needed to raise 1 gram of that substance 1 degree C. We will most commonly be using water. Water is a liquid, has a specific heat of 4.18 joules for every 1 gram 1 degree C. Ice has its own specific heat. Gaseous water has its own specific heat. Okay, now do not be fooled here. Specific heat is gram per degree C. Molar heat capacity is the amount of heat needed to raise 1 mole of a substance 1 degree C. I'm going to assume, and I think it's a correct assumption, that you can interchange between these. If you are given grams and you're only given the molar heat capacity, you could probably use this equation easily. What did I skip here? All right, substances respond differently to being heated. You know that. The heat capacity of anything is the heat absorbed over the increase in temperature. Something that has a high, this is where kids get confused. Something that has a high heat capacity, big numerator, means that, and a little denominator, means that you can put a lot of heat into it before the temperature changes. All right. Constant pressure calorimetry means that this is open to, this is not a completely closed system, and so the pressure cannot change. So we're good to go to use my favorite MCAT. Knew there had to be a cat reference. Somewhere. Peanut got herself stuck in a TV box in a closet for most of the day. The TV box was this wide. Peanut is this wide. She's kind of like stuck halfway in the top of the door. Huh? She's a midget. She really is. Her legs are this long. It's very, very adorable. I'll show you a picture later. Not while we're filming. Okay, so Q equals MCAT, where Q is the heat absorbed or released. Thank you for filling him in. Like, who's Peanut? The famous Peanut. M is a mass, extensive property. C is the specific heat capacity, which is dependent on the substance. And T is the change in temperature. Please remember, it is final minus initial. Final minus initial. Okay, I'm just going to mention this because it's kind of cool. Constant volume calorimetry is different than constant pressure calorimetry. How? It deals with something called the bomb calorimeter. How cool is that? It actually looks like a bomb. It has a little neck and it's round and it's rigid. This part cannot change at all. Okay, you have a top on it. And each one of these, this container itself, the bomb calorimeter, has a heat index in it. I can't remember what this is called because I don't use it very often. A heat index, and it's going to tell us how much heat it can absorb. You put stuff in there and you combust it.
Does it blow up?
It depends what it is. Depends what it is. If it's your food, no. But if it does blow up, it cannot change the volume. What happens if it blows up? The pressure goes up, so what happens to the temperature then? It goes up too. So the amount of heat released during the combustion can be measured, and you can tie that into the number of kilocalories that each food, like if you took a Cheeto, put it in there and flambéed it, you could figure out how many kilocalories are in a Cheeto. And really, this is how, you know all those nutritional facts on the side of your food? I believe someone, some way did. Can we do it?
Yep.
You did do it. In Chem 1, remember a Coke can and the Cheeto, and it smelled really, really awful?
What is the thing?
A metal. In real life, not a Coke can in our ghetto world. Okay, now, you know what? I didn't do this, but you have to deal with it. Look at this. Delta H ought of formation. Really? Are you kidding? The standard enthalpy for the formation of a substance. What are you talking about? Here is what I'm talking about. If you took some carbon and you reacted it with half a mole of oxygen, it would form carbon monoxide. Wait a minute, you say, a half a mole of oxygen? Are you crazy? It has to be a whole number. Okay, we're looking at the formation of the carbon monoxide. The enthalpy of formation is always for 1 mole of the substance we're talking about. We're talking about 1 mole of carbon monoxide. Okay, somebody has figured this out for us. How much heat was either absorbed or evolved when this reaction occurred to figure this out. This ought sign, stand by for confusion, in 3, 2, and 1, denotes standard conditions. Standard conditions is not STP. Standard conditions mean what you would find in the real world. Standard condition is 25 degrees C, which is room temperature, 1 atm, which is the atmosphere at sea level, and a concentration of 1 molar. The delta H of vaporization is the amount of heat needed to convert a substance from a liquid to a gas at its normal boiling point. The delta H of fusion, converting a substance from a solid to a liquid at its normal melting point. The delta H of combustion is the enthalpy for combusting a substance in oxygen. And the delta H of reaction is the heat lost or gained during a chemical reaction. Okay, I will be giving you the enthalpy charts. I wish I had put them out, but I didn't. I forgot to put them out. But that's okay. All right. So now we're on the third way that you can figure out delta H, and that's for looking at the delta H ought of formation, the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements. Get it? All substances are in standard state. Here it is right now. Now, if you have your highlighter, I need you to do something for me. For an element, if we're talking about an element, the state of matter for that element that the element exists at 25 degrees C. So if we were talking about bromine, it would be a liquid. All elements have a delta H ought of formation equal to 0. Why, you might ask? Because you know what? They got really tired of figuring all this out, and they figured, you know what? The elements were just here. So we don't know how much energy it took to form them, so we're going to say it's nothing. Here it is, one more time. The enthalpy of a reaction is equal to the sum of the enthalpies. Look, I forgot my little ought sign. Of the delta H ought of formation of the products minus the sum of the delta H ought of the reactants. Really, what I want you to get out of this is delta H is products minus reactants. Products minus reactants.
Same thing as temperature and
Yep. All elements have a delta H ought, a formation of 0. Now, if in a reaction you have 2 moles of something, you have to multiply delta H ought of formation by the same coefficient, which would be 2. So if 1 mole of water, when it's a liquid, has a delta H of formation of this, 2 moles would have 2 times that. Got it? That is so intuitive. I got it right away. Okay, for me, these problems are a nightmare because I will make a math error somewhere along the line and get a totally wrong answer, and it's enough to make me bonkers. So I'll be doing this the long way. See if you're like that as well. Sample problem D. Calculate the delta H aught of reaction for the following. So here you go. Delta H reaction, products minus reactants. Products minus reactants. So I have a balanced equation there. Don't be fooled. You don't balance it, your numbers aren't right. And I know that it is products minus reactants. I'm just going to go ahead and list the products right now because there are 1, 2, 3, 4 of them. I have aluminum oxide, and I have aluminum chloride, and I have 3 nitrogen monoxides, and I have 6 waters. Warning, warning, warning. There are different values for water. And there are different actually there's different values of everything depending on their states of matter, so we better put them there. Okay, somebody has to give you this. Yes?
That's gas.
This is gas?
The water.
Water's gas? Okay, thanks. Somebody has to give you these values. Nobody expects you to mesmerize them. Now, that was just the products minus the reactants. 3 aluminums plus, name this for bonus points.